Question 12, Part D. Note that to answer this question, the perpendicular distance formula is required. Now the perpendicular distance, d, of the point x1, y1 from the line ax plus by plus c equals 0 is given by d equals the absolute value of ax1 plus by1 plus c over the square root of a squared plus b squared. The point P, t, t squared plus 3 lies on the curve y equals x squared plus 3. The line L has equation y equals 2x minus 1. The perpendicular distance from P to the line L is d of t. Part 1. Show that d of t equals t squared minus 2t plus 4 over the square root of 5. In order to use the perpendicular distance formula, we need the equation of line L in general form. Currently, it's in gradient intercept form, that is y equals mx plus c. So rearranging the equation of line L so that it's in general form, we get 2x minus y minus 1 equals 0. Now the perpendicular distance of point P at coordinates t, t squared plus 3 from line L is given by d of t is equal to the absolute value of 2t minus t squared plus 3 in brackets minus 1 over the square root of 2 squared plus negative 1 in brackets squared. So expanding the brackets here and evaluating the expression inside the surd here, we get d of t is equal to the absolute value of 2t minus t squared minus 3 minus 1 over the square root of 5. So at this point, we have the denominator that we want. We just need to clean up the numerator. So collecting the like terms, we have negative 3 minus 1. We get d of t is equal to the absolute value of 2t minus t squared minus 4 over the square root of 5. Now if we factorize out the negative from all three terms, we get the absolute value of negative or minus bracket t squared minus 2t plus 4 close bracket over the square root of 5. Now when we take the absolute value of a negative, it turns it into a positive. So we can get rid of the absolute value brackets and the negative symbol here, and we get d of t is equal to t squared minus 2t plus 4 over the square root of 5 as required. Part 2. Find the value of t when P is closest to L. Looking at this graphically or geometrically, the graph of y equals d of t, where d of t is equal to t squared minus 2t plus 4 over the square root of 5, is a concave up parabola with the vertex at t equals 1. Now the vertex of a concave up parabola represents the minimum value of the function, in this case d of t, and d of t is the distance from point P to the line L. So how do we get t equals 1? Now the x-coordinate of the vertex is given by the formula negative b over 2a, where b is the coefficient of the term involving t, and a is the coefficient of the term involving t squared. So in this case, our b is negative 2, so negative 2 gives us positive 2, which is why we get 2 in the numerator here. And in the denominator, we get 2 times the coefficient of t squared, which is 1. So 2 times 1 is 2, and 2 over 2 is equal to 1. Therefore, P is closest to L when t equals 1. Part 3. Show that when P is closest to L, the tangent to the curve at P is parallel to L. From part 2, the x-coordinate of point P when P is closest to line L is x equals 1. So we need to show that the gradient of the tangent to the curve y equals x squared plus 3, where x equals 1, is equal to the gradient of line L. Now recall the equation of line L is y equals 2x minus 1, and it's in the form y equals mx plus c, or in gradient intercept form. So from the equation, the gradient of line L is the coefficient of x, which is 2. Now in order to get the gradient of the tangent to the curve, we need the gradient function of y equals x squared plus 3. And we get that by differentiating y with respect to x. So y dash is equal to 2x. Now at x equals 1, the value of y dash is equal to 2. So 2 times 1 equals 2, which equals the gradient of line L. And if the gradient of the tangent is equal to the gradient of line L, that means they're parallel. Therefore, when P is closest to L, the tangent at P is parallel to line L.